Hello friends. So today we are going to discuss questions from the modern physics. And these questions are from the year 2002. A total of 4 questions. And from the year 2003, a total of 7 questions. So in totality, we are going to discuss 11 questions. So in the first question, which was asked in the year 2002, and it states that a hydrogen-like atom described by the Bohr's model is observed to emit 6 wavelengths originating from all possible transition between a group of levels. These levels have energy between minus 0.85 electron volt and minus 0.544 electron volt, including both these values. Take Hc, product of H and C, as 1240 electron volt. Ground state energy of hydrogen atom is minus 136 electron volt. So based on this, two things are asked in part number A: find the atomic number of the atom, and part number B: calculate the smallest wavelength emitted in this transition. So in this case, we are given first of all that it is emitting 6 wavelengths. So we start from there only. So we can say total wavelengths emitted is equal to 6. So basically means that there will be 6 transition lines between various levels. So you can say total transition lines will be equal to 6. Okay, and these can be from any level to any level. Okay, but total count will be always 6. So we know the basic formula for the total transition lines, and that formula is our n times n minus 1 divided by 2 is equal to 6. So from here we can say that our value of n is equal to 4. So it means between 1 second. Yeah. So it also states that the energy level between is minus 0.85 and minus 0.544, and both values are included. So it means if we are taking extreme levels, and this extreme level is going to have a, you can say, minus 0.85, and other one will be our minus 0.54. Okay. This will be our minus 0.544, and the other level will be minus 0.84, because it says inclusive the other lines, and in totality this will be our 4. So if we can say that the transition takes place between, suppose this is the mth level, then automatically the lastmost level, uppermost level, will be our m plus 3. Okay, because the total will be our 4. Okay. So we can say that transition is taking place between mth energy state and m plus 3th state. So therefore we can write that for mth energy state our E of m will be equal to minus 0.85, not 84, sorry, this was 85, and the general formula also we know, then this will be equal to minus 13.6 z square, and state is our, in this case, our m, so n will be replaced by m, so it will be coming as m square. So from here we can easily find out the ratio of z upon m, and that ratio of z upon m will be equal to 0.25. Similarly, for our E m plus 3, and that is equal to minus 0.544, and this will be equal to our minus 13.6 our z square and m plus 3 whole square. So from here we can write that our z upon m plus 3 will be equal to 0.2. So let us this be our equation number 1 and this be our equation number 2. Now if we solve equation 1 and 2, from equation 1 and 2 we have two unknowns and two equations, we can easily find out value of z and m. So we are going to get value of m is equal to 12 and value of z is equal to 3. So this is our first part. We were supposed to find out the value of the z, that is our atomic number. Then it states that calculate the smallest wavelength emitted in this transition. Now we already know that so we are having this is our m plus 3 and this is our m, and in between this will be first and second, so 1, 2, 3 and 4. Okay. And the transition, we can just draw the transition lines. Total transition line will be giving us 6. So this will be 1, 2, 3, 4, 5 and 6. Okay. So obviously the smallest one will be the difference in the energy, and energy difference we already know, that is given to us as minus 0.85 and this is our minus 0.544. So this is going to give us a smallest lambda. That is the smallest wavelength. So we can say our part B. We can use the energy relationship between the wavelength and the energy. So you can say our delta E will be equal to hc upon lambda, and we can write this will be equal to 0.85 minus 0.544, and we have this is hc upon lambda, and we already given this will be coming as hc, and we have here 0.85 minus 0.544, and Hc is having in terms of electron volt is our 1240. So we get this as 1240, and this will be 0.85 minus 0.544. So from here we get our lambda is approximately equal to 4052 nanometers. So atomic number, that is value of Z, is our 3, and the smallest wavelength is our lambda. Next question. It was also asked in the year 2002 and states that two metallic plates A and B, each of area 5 into 10 to the power minus 4 meter square, are placed parallel to each other at separation of 1 centimeter. Plate B carries a positive charge of 3 into 7 into 10 to the power minus 12 coulomb. A monochromatic beam of light with photons of energy 5 electron volt each starts falling on plate A at a time t is equal to 0, so that 10 to the power 16 photons fall on it per square meters per second. Assume that one photoelectron is emitted for every 10 to the power 6 incident photons. Also assume that all the emitted photoelectrons are collected by plate B, and the work function of the plate A remains constant at a value of 2 electron volt. Determine. So in this case we are going to find out 4 things. The number of photoelectrons emitted up to t is equal to 10 seconds. The magnitude of electric field between plates A and B at t is equal to 10 seconds. And finally, the kinetic energy of the most energetic photoelectron emitted at t is equal to 10 seconds when it reaches plate B. So first of all, we are going to find out the total number of photons, total number of incident photons rather, and that depends upon the photons per unit area multiplied by area along with the time. So we can say that total number of incident photons let us suppose that is given as n incident, then we can write that our n incident will be equal to photons per unit area per unit time. Per unit area per unit time multiply by area and multiply by time. So we are given that we are having 10 to the power 16 and area is our 5 into 10 to the power minus 4 and time is our 10 seconds, and this comes as our 5 into 10 to the power 16, sorry, not 6, 13. So these are the number of incident photons. Based on this, we can easily find out number of photoelectron emitted. So you can say number of photoelectron emitted let us call this as n emitted, and this will be equal to total incident photons, which is our n incident, and divided by emission ratio, that is our 10 to the power 6. emission ratio. So we get our number of electrons emitted, n emitted, will be equal to n incident is our 5 into 10 to the power 13, emitted ratio is our 10 to the power 6. So this gives us 5 into 10 to the power 7. So these are the number of photoelectrons emitted. And we have to find out the charge after time t. So we can say that charge on plate A at t is equal to 10 seconds. Let us call this as QA. So we can write our QA will be equal to number of photoelectrons emitted multiplied by charge on one electron. So this comes as 5 into 10 to the power 7, and this is 1.6 into 10 to the power minus 19. So we get charge on plate A will be equal to 8 into 10 to the power minus 12 coulombs. And it is also given that our plate B collects all the electrons. Okay. So obviously, because previously the charge on this plate B is said to be a positive, and that is given as 33.7 into 10 to the power minus 12 coulomb, and it is positive. So as it is going to collect more and more electrons, the charge on this is going to reduce. We can just draw an approximate figure also. Suppose this is plate B and this is plate A. So as the light is incident on it, it is going to emit electrons, and those electrons will be collected by plate B. Okay, and we found out, and as it is going to emit electrons, our plate A is going to have a charge of, that is our QA, whose will we just found out, and the same charge will be accumulated by, collected by plate B. Okay. Initial charge we assume that on plate B is our QB. Final charge after 10 seconds will be our original charge minus the charge that is being collected by plate B, because for time 10 seconds. So we can write that plate B collects electrons, so its positive charge decreases. Its positive charge decreases, which basically means that the new charge, or rather you can say the charge on plate B at t is equal to 10 seconds, let us suppose that is QB prime. So the value of QB prime will be equal to original charge, that is QB, minus the charge it's collecting, that is our QA, and this comes as 33.7 into 10 to the power minus 12 minus 8 into 10 to the power minus 12. So we get that our QB prime will be equal to 25.7 into 10 to the power minus 12 coulombs. That was the, so we found out the number of photoelectrons emitted up to 10 second, that is our 5 into 10 to the power 7. And part B, we are supposed for electric field. Okay, so we found out the charge respectively on plate A as well as plate B. So after 10 second, we can just redraw the figure again. After 10 second, the charge on plate B is QB prime and charge on QA is our QA. Okay, that because that is a charge it got after time t is equal to 10 second. So therefore, if E is the electric field between the two, so we can write that the electric field now in this case it is something like a two parallel plates, and those parallel plates are having a different charge. One is QA and other one is QB prime. So we are going to find out the mean of the charges. Okay. And this QB is said to have a positive charge, rather we can say QB was positive. QB prime will be also positive because on a lower less value, and this QA will be our, one second, this will be our value is given to us 8 into 10 to the power minus 12. So we know the value of QA as well as QB prime. So therefore we get the electric field between two parallel plates with charges QB prime and QA. Let us suppose that electric field is given as E. Therefore we can write that our electric field E will be our charge on the plates, that is QA minus QB, sorry, QB prime minus QA divided by 2 and 1 upon 2 epsilon naught. And we already know their values, we simply substitute them. Sorry, this is A, not 2. And we substitute the values. QB prime is our 25.7 into 10 to the power minus 12, and QA is our 8 into 10 to the power minus 12 divided by, we have this is 2, area we know is our given to us 5 into 10 to the power minus 4, and epsilon naught value we know is our 8.85 into 10 to the power minus 12. So we get that the value of electric field is our approximately 2 into 10 to the power 3 Newton per Coulomb. And part C, kinetic energy of the most energetic photoelectron is emitted at T is equal to 0. So in this case, we are basically going to find out our kinetic energy based on our initial kinetic energy, and then we are going to find out the final kinetic energy based on the combination along with the work done. So we start with our initial kinetic energy. Initial kinetic energy of most energetic photoelectron. Energetic photoelectron, and let us call this as K initial, Ki, that will be equal to our energy of the photon minus the work function, and this is our 5 minus 2 giving us 3 electron volt. And then we are going to find out the work done by the electric field on the photoelectron. Work done by the electric field on photoelectron, suppose that is given as W, then we can write that our W is equal to charge multiplied by electric field multiplied by distance, and that values are given to us. So this is 1.6 into 10 to the power minus 19. Electric field we already found out is 2 into 10 to the power 3, and distance is our 10 to the power minus 2 meters. So we get our work done will be equal to 3.2 into 10 to the power minus 18 joules, and we are going to convert this into electron volt. So best is if you multiply this term as 1.6 into 10 to the power minus 19, and this comes in electron volt. So here this 1.6 and 1.6 cancel directly, so we get that work done will be equal to 2 into 10 raised to power 1, or basically we can write 20 electron volt. Okay, so this is the work done in electron volt. So final kinetic energy will be equal to initial plus work done. So we can write that one second. Yes, so it asks for the kinetic energy when it reaches plate B. So at plate B will be equal to its initial kinetic energy, because that is going to gain as the, you can see, incident light will be forcing it to move some with energy, which we found out according to the work function equation. And second will be that the work done it does because of the electric field. Therefore we can write that kinetic energy of the most energetic photoelectrons at plate B. Let us call this as Ke final. This will be equal to our Ke initial plus work done. Ke initial is our 3 electron volt, and this is about 20, giving us 23 electron volt. So this is our final answer, and we are supposed to find out electric field, which we found out, and we were supposed to find out the number of this that we already solved it. Next question. It was asked in the year 2002, and it states that the half-life of 21580 is 100 microsecond. The time taken for the activity of a sample of 21580 to decay to 1/16th of its initial value is. So we are given half-life of the sample. So we can write that T half is given to us as 100 microsecond, and it says that it decays to the 1/16th of initial value, or we can write it as activity decays to 1/16th of initial value. So directly we can use the activity formula. So we can say that our decay formula for activity and that formula gives us that our A is equal to initial activity A naught multiplied by 1/2, and this comes as 1 upon T half, and the relation between the activity and its initial value is given as 1/16th. So we can say that our A is equal to 1/16th of initial value, which is our A naught. So we can write that our 1/16th A naught is equal to A naught 1/2, and this is our T half is known to us, that is our 1 upon 100. Sorry, this is T upon T half, my mistake, not 1 upon. And this A naught and A naught cancels out. So we can just manipulate it. 1 upon 16 can be written as 1 upon 2 raised to power 4 is equal to, this comes as 1/2, and we have this is T upon 100. This gives us that T upon 100 is equal to 4. And from here we get our T is equal to 400 microsecond. So option number A is correct. Next question. It was also asked in the year 2002, and it states that the potential difference applied to a X-ray tube is 5 kilovolt and the current through it is 3.2 milliampere. Then the number of electrons striking the target per second is. So in this case we are going to find out number of electrons, and we are given the current. Based on current we can find out our charge, that is Q, and from there we are easily going to find out our number of electrons. So we are given voltage, that is our V is our 5 into 10 raised to power 3 volts, and current, that is our I, it is also given as 3.2 milliampere. So we can just use the relationship between current and charge. We know that our current I is equal to Q upon T. And from here we can write our Q is equal to current multiplied time T. And it is asked our per second. So value of this will be equal to 3.2 into 1, giving us 3.2. And the number of electrons per second, number of electrons per second, let us suppose that is our N, will be equal to total charge Q divided by charge on 1, and total current is our, sorry, it is milliampere minus 3. So this comes as 3.2 into 10 to the power minus 3 divided by 1.6 into 10 to the power minus 19. So this gives us that our number of electrons, that is our n, will be equal to, this comes as 2 into 10 to the power 16. 2 into 10 to the power 16, option A is correct. Next question. It was asked in the year 2003, and it states that in a photoelectric experiment setup, photons of energy 5 electron volt fall on cathode having work function having work function 3 electron volt. So in part A, if the saturation current IA is 4 microampere for intensity of 10 to the power minus 5 watt per meter square, then the plot a graph between anode potential and the current. And part B, also draw the graph of intensity of incident radiation 2 into 10 to the power minus 5 watt per meter square. So in this case, we are given a saturation current, and based on this saturation current, we are also given the energy of the incident photon, that is our photon energy, that is 5 electron volt. And work function is given to us as 3 electron volt. So we can say photon energy that is our E photon is equal to 5 electron volt. We are having a work function phi, it is given as 3 electron volt. So we can write that the maximum kinetic energy of emitted electrons, maximum kinetic energy of emitted electrons, that is our K max, will be equal to our E photon minus the work function. So we can just substitute the values. E max will be equal to our 5 minus 3, giving us 2 electron volt. And it is said that the saturation current for intensity 10 to the power minus 5. So let us call this intensity as I1. So we can say saturation current for intensity, let us suppose that intensity of I1 will be equal to 10 to the power minus 5, and the value of saturation current is, suppose small I1 is given as 4 microampere, and the new intensity is said to be 2 into 10 to the power minus 5. So we can say that our new intensity let us suppose that is of I2, it is given as 2 into 10 to the power minus 5. So if you make a comparison between our initial intensity I1 and final intensity I2, yeah, new intensity I2, that is almost double. So we can say that I2 is equal to twice of I1. Therefore, we can say that the photo emission rate doubles, also double. So we can say this will double the photo emission rate also. And from here we can also say the saturation current will also increase, means double. Saturation current will become, suppose that saturation current is given as I2, and that will be equal to twice our I1, which is our 8 microampere. And we are supposed to find out anode potential, also draw graph intensity. Okay, so we have to plot the graph for both the values. From the calculation we can easily see that our saturation current becomes double, and our stopping potential is our 2 electron volt. That is our, so we can say that our stopping potential is our 2 volts, and this is magnitude wise, actually it will be our -2. And so we can just easily plot our required graph. So here we have a anode potential, that is our V, and this is our saturation current, that is our I. And in both the cases the stopping potential is same, whereas our saturation current is different. So this is our 4 microampere and this will be 8 microampere, and we are going to get this value will be our -2 volts. Next question. It was asked in the year 2003, and it states that a radioactive element decays by beta emission. A detector records n beta particles in 2 seconds, and in next 2 seconds it records 0.75 n beta particles. Find mean life of radioactive element given that natural log of 2 and natural log of 3 values are given to us. And it says that the element is by the emission of our decay by beta emission. So we are given that decay is via beta emission. And in the first 2 seconds, the detector records n beta particles. Records n beta particles, and in next 2 seconds next first 2 seconds, next 2 seconds the detector records excuse me please 0.75 n beta particles, and we have to find out the mean life, that is about tau. And we start with the standard equation of the activity, and we say that initially at t is equal to 0 the undecayed nuclei is suppose n naught. We can say let the number of undecayed nuclei at t is equal to 0 is n naught. So therefore we can say activity at time t it can be written as a of t, and that will equal to minus dn upon dt, and that will be equal to our lambda times nt, and we can further write it as that a of t will be equal to lambda times nt and is equal to lambda times substituting value of this equation for nt, that is of n naught e raised to power minus lambda t. And we have to find out the number of beta particles, that is decay. So we are going to find out calculate the number of beta particles decays, and these beta particles are having two different, you can say, values. In first interval and that first interval starts from 0 and go up to 2 seconds, and during this interval we are given that the number of beta particles is n. Therefore we can write the equation that our n, small n, will be equal to our n naught 1 minus e, and this is minus lambda times 2. And we have a second interval, and that second interval starts from 2 and ends at 4 seconds. And in this case, first of all we have to find out the remaining nuclei at t is equal to 2 seconds. Remaining nuclei at t is equal to 2 seconds, and that will be equal to over n naught e raised to power minus 2 times lambda. Now we can find out the decay in next 2 seconds. Decay in next 2 seconds, and that value is given to us as 0.5 times n, 0.75 n will be equal to over n naught e raised to power minus 2 lambda, and this comes as 1 e raised to power minus 2 lambda. And here we can clearly see the distinction between, for the first interval the initial was n naught, whereas for the second interval, that is from t to 4 seconds, the initial value is our n naught e raised power minus 2 lambda. So this is a basic distinction between the two. And we can just find out the ratio now. And you can say ratio, we get this as 0.7n divided by n will be equal to, we are having this is n naught e raised power minus 2 lambda 1 minus e raised power minus 2 lambda and divided by n naught 1 minus e minus 2 lambda. Here this n and n naught and this all everything goes away. So only term that is left is our e raised power minus 2 lambda. So we can write this as 0.75 is equal to e raised power minus 2 lambda. And this can be further written as natural log of 0.75 is equal to minus 2 lambda, and we get from here that our lambda will be equal to natural log of 0.27 is our minus 0.2877 divided by minus of 2. Obviously minus and minus goes away, so we get our lambda is equal to 0.14385 per second. So we got the value of lambda. And now the mean life formula. So we can say mean life, that is our tau is equal to 1 upon lambda, giving us 1 upon 0.14385, which gives us approximately equal to 6.95 seconds. Next question. It was also asked in the year 2003, and it states that characteristics X-rays of frequency 4.2 into 10 to the power 18 Hz are produced when transition from L shell to K shell takes place in a certain target material. Use Mosley's law to determine the atomic number of the target material given Rydberg constant is 1.1 into 10 to the power 7 meters. So it is straightforward ask that we have to use the Mosley's law. And we start from there only. So we can say Mosley's law for our X-ray states that the frequency, that is our nu, is equal to R multiplied by C, and this comes as Z minus 1 whole square, and here we have transition is from L shell to K shell. Okay, so we can write this as, let us suppose this comes as our K square and 1 minus our L square with respect to their shells, and we can just substitute the values. We get our nu is equal to, and Rydberg constant is given to us. Rydberg constant is our, one second, frequency is also given to us. Frequency is 4.2 into 10 to the power 18. Rydberg constant is given as 1.1 into 10 to the power 7. Speed of light, that is c, is our 3 into 10 to the power 8, and this comes as z minus 1 whole square, and we have this as k k will be over 2, sorry, k will be over 1 and L will be over 2. So this comes as 1 minus 1 upon 4. So we can just straightforward sort it out, and we get this as, this will be equal to over 3 by 4. So we get our z minus 1 whole square will be equal to 4.2 into 10 to the power 18, and this comes as 1.1 into 10 to the power 7 into 3 into 10 to the power 8 multiply by 4 and divide by 3. So this will be approximately equal to 1696.97, and we get from here that our z minus 1 will be equal to square root of 1696.97, approximately 41.2. So we get value of z will be equal to 41.2 plus 1, and this gives us z is equal to 42.2, which were atomic number that we is 42.2. Next question. It was also asked in the year 2003, and it states that if the atom 100 to 257 follows a Bohr's model and the radius of the last orbit of 100 to 257 is n times that of Bohr radius, then the value of n is. So this is quite straightforward. The relation between our last and our Bohr model is given to us. Okay, so for the we can say that atomic number of our FM 100 to 257, let us suppose that is our Z, will be equal to 100. And we can just write the electronic configuration of this FM. So we can say our electronic configuration of FM, that will be over 2, 8, 18, 32 and 50. So it means the last orbit number, if that is represented as m, and that will be equal to 5. Okay, 1, 2, 3, 4 and 5. And we can use the Bohr radius formula. Bohr's radius formula, which states that for the last orbit, if radius is given as r of m, because we have assumed that the last orbit is represented as m, then this will be equal to our m square divided by z multiplied by our r naught. And we substitute the values, so we get our Rm will be equal to 5 square and z is over 100 multiplied by R naught, and this gives us our R naught upon 4. And we are given that the radius of last orbit is n times that the Bohr radius. Bohr radius of R naught and last orbit is Rm. So you can see from given conditions we can write that our Rm is equal to n times R0, and we also found out that our Rm is equal to 1 upon 4 times R0. So if we make 1:1 comparison between these two, this gives us that value of n is equal to 1 by 4. So option number D is correct. Next question. It states that the electric potential between the proton and the electron is given by V is equal to V naught natural log of R upon R naught, where R naught is a constant. Assuming Bohr's model to be applicable, write the variation of Rn with n. Here n is the principal quantum number. So we are given that potential relationship between the proton and electron is given to us, and from there we are going to find out the, you can say, relationship, because from the potential we are going to find out the force, and this force is going to provide the centripetal force, and from there we can sort it out. So we are given that V of R given equation is equal to our V naught natural log of R upon R naught, and our, we can say, energy force relationship energy force relationship. In Bohr model, the force is providing our centripetal force, so we can write, or we can say, the centripetal force if that is our F, then this F will be equal to our mv square upon R. And we also know the relationship between the force and the potential. So we can say the force F will be equal to minus dV upon dr. We substitute value of our potential, that is our V naught natural log of R upon R naught, and we can just, V naught will be our constant, so we can just take it outside, and this will be our minus V naught d upon dr. Inside we will be left with only natural log of R upon R naught, and that can be written as natural log of R minus natural log of R naught. And we are given that R naught is constant, so its derivative vanishes. And natural log of R will be giving us 1 upon R. Therefore, we get this will be equal to minus V naught upon R. And the centripetal force, and this force is, you can say, electrostatic force, okay, because we derivated our with respect to distance. So we can write that our centripetal force is equal to our electrostatic force. So if we equate them, we get our mv square upon r will be equal to our v naught upon r, and here this r and r cancels out, so we get our v naught is equal to m v square. So our v will be equal to square root of v naught upon m. V naught is a constant, m is also constant, therefore we can say that our velocity is independent of r entirely from this equation, or we can say this is constant. So therefore, if we use our quantization of angular momentum, quantization of angular momentum, that is our Bohr quantization, so we can write our mvr is equal to n times our h. So this gives us our r is equal to nh divided by our mass into velocity. And we just proved that our velocity is constant, mass is, we proved velocity is constant, mass is always constant, and Planck's constant is constant. Therefore from here we can say our r is directly proportional to n, or we can say for nth we can call this as Rn. So Rn is our directly proportional to n. So option number A is correct. Next question. It states that a nucleus of mass number 220 initially is at rest emits an alpha particle. If the Q value of the reaction is 5.5 mega electron volt, calculate the kinetic energy of the alpha particle. So we are given that the nucleus is having a mass number of 220, which we can just call it a parent. So we can say parent nucleus atomic number, sorry, not atomic number but mass number. Mass number, that is of A, it is given as 220, and it says that it emits alpha particle. Emits alpha particle, or mass number four, and we are given Q value during this entire emission process. Q value is the thing, basically total energy released. Total energy released, and that is given as our Q, which is 5.5 mega electron volt, and it says that initially the parent nucleus is at rest. Okay. So parent nucleus is going to emit alpha particle, so we can say parent nucleus is equal to daughter nucleus plus alpha particle. So we can say our decay process and decay process states that our parent nucleus gives us daughter nucleus plus alpha particle. And from here we can find out the mass number of the daughter nucleus. You can say mass number of daughter nucleus let us call this as AD, that will be equal to parent nucleus is 220 and alpha is 4, so 220 minus 4, so we get our AD is equal to 216. And we can just use the conservation of momentum and solve it. So we can say that conservation of momentum and parent nucleus was initially at rest, therefore you can say that our momentum of alpha particle will be equal to momentum of the daughter nucleus. And we already know relation between kinetic energy and momentum, that our kinetic energy K is equal to momentum square divided by 2m. So we can write that our this can be divided in two parts. Kinetic energy of alpha particle will be equal to p square upon alpha divided by mass of alpha, and we can write kinetic energy for daughter is equal to p square of daughter, this is twice mass of daughter. And it is, we just wrote that our p alpha is equal to pd square, or we can just take the ratio, we can sort it out later. So we get our k alpha upon k daughter will be equal to, we have here p alpha square upon 2 mass of alpha, and we have pd square upon twice mass of daughter. Pd and p alpha cancel, 2 and 2 also goes away, so this gives us mass of daughter divided by mass of alpha. Mass of daughter is 216, mass of alpha is over 4, so this gives us 54. So we get from here that our kinetic energy of the daughter will be equal to kinetic energy alpha divided by 54. Now we can also use that the total kinetic energy will be equal to the energy released. So we can say total kinetic energy is equal to value of Q, and total kinetic energy is kinetic energy of alpha plus kinetic energy of daughter, and parent was at rest, so its value will be 0, is equal to Q, which is 5.5 mega electron volt. And we already know between K alpha and K, we found out, we just substitute it, we get this as K alpha plus K alpha upon 54 is equal to 5.5, and we can take K alpha is common, so this comes as 1 upon 54, so this comes as 55 upon 54 is equal to 5.5, and we get our K alpha is equal to 5.5 into 54 divided by 55. This gives us approximately equal to 5.4 mega electron volt. This comes as 5.4 mega electron volt. Option B is correct. Next question. It was asked in the year 2003, and it states that for uranium nucleus, how does its mass vary with the volume? And basically this is quite standard relationship, or we can say that the mass of a volume of a nucleus is proportional to number of nucleons, that is our A, and density of the nucleus is more or less, we can say, constant. You can say that density of the nucleus is constant. So we can directly write that the mass is directly proportional to the volume. Option A is correct. Correct. So this completes the questions from the year 2002 as well as 2003. Thank you.